Hello, good morning, students. Can you hear me?
Sir,
Okay. So, guys, last class we have finished chemical kinetics, and today we are going to start with solid state. Correct? Okay, we'll wait for a few more minutes. Let others also join. Okay, good morning, all of you. Let's start the session today. We are going to start with solid state. Okay, as we discussed last class, we have finished chemical kinetics. Okay. See, when we talk about the states of a matter, okay, because solids is nothing but a state of a matter, right? Any object, any matter, normally it exists in three different states, right? At normal temperature, normal condition, three different states we know. It is solid, liquid, and gas, okay? Solid, liquid, and gas. Three different states we have here. Why we have these three states, first of all? What is the reason behind this three states? Are these states interconvertible? Yes, they are interconvertible. We can take the example of water. Water can be converted into its gaseous form, that is vapor, and it can also be converted into solid, that is ice. Okay, all these three forms, solid, liquid, and gas, are interconvertible. First of all, okay, we can convert liquid to gas, liquid to solid, solid to gas. All these things are possible. Okay, now what is the change? What is the change happen when one particular matter, one particular state converts into the other state? Like if solid converts into liquid, what is that factor which changes into these two things? When liquid converts into gas, what is that factor that changes? Okay, and the major factor is, the intermolecular force of attraction. Force of attraction. In short, we write it as IMF, intermolecular force of attraction. Okay, when we talk about IMF, In solids, we have maximum IMF. It is very strong intermolecular force. Right? In liquid, it is weak IMF. And gas, it is very weak. Okay? And because of weak intermolecular force means not between the atoms or among the atoms there are forces. Suppose we have an object, any solid object. Suppose you have pen in your hand right now. Okay, so there are atoms of that particular object, that is pen, right? Atoms are bonded together with a very strong intermolecular force if the object is in solid. When we talk about a gas, right? Suppose in a container, gas is present, right? So there are gaseous molecules present in it, right? All these gaseous molecules interact with each other. You see, these are the interaction among the gaseous molecules. All the interaction. This interaction is very weak in case of gases. And that is why these atoms have random motion. They move randomly in all directions. Gaseous particles move randomly in all directions. Okay? Because of very weak intermolecular force. Their motion is possible in all directions. It is not affected by the another gaseous particles present in it. Okay? This particle, if you talk about it, can move in this direction, in this direction, in this direction, in this direction, all direction actually. Okay, because it is not bonded with a strong intermolecular force. If this force is strong, then this force won't let the atom to move in any direction. Okay, but this kind of motion we do not observe in a solid object because the atoms are bonded with a very strong intermolecular force. Okay, like I said, liquid, the intermolecular forces are weak. That's why water can flow. Okay, that's why water can flow and occupy the shape of the vessel in which it is poured in, right? Gaseous particles has very weak intermolecular force, occupy the volume of the container in which it is present. Okay, the entire volume of the container, the volume of the container is nothing but the volume of the gas, right? Solid particles has a fixed volume and fixed shape. Okay, all these basic definition you must know, right? So this is the three different states of matter we have. How can we change these three states of matter? You see, the gaseous particles have very weak intermolecular force, right? So if you keep on increasing, you'll get a range of intermolecular force, right? You'll get a range, and then the gas starts converting into liquid. Means what I'm trying to say, gaseous particles have a fixed range of intermolecular force. Suppose this is the range we have. When the intermolecular force falls in this range, the state of the matter will be gas. Okay, whatever the range we have here. Similarly, we have a range for this liquid also, and we have a range for this solid also. Okay, so when the intermolecular force falls in this range, the state of matter is gas. If this range is there, then it is liquid. For this, it is solid. Okay, you keep on increasing the intermolecular force. Okay, what I'm telling you, if keep on increasing the intermolecular force, when the intermolecular force increases or it comes out of this range and falls into this range, then the gas starts converting into liquid for this range, right? If you keep on increasing the intermolecular force, if the intermolecular force falls in this range, by increasing it, the gas starts converting into liquid. Further, if you increase and if it falls in this range, the liquid starts converting into solid. So this happens when IMF increases continuously. IMF increases continuously. Similarly, this is true in other way also. Decrease IMF, you'll get liquid first and then you'll get gas. Okay. Understood this? So the basic reason for the three different states of matter at normal temperature is the intermolecular force of attraction. Okay. Now, today the chapter we are going to study is solid state, right? Our concern with this chapter, this particular state, solid state, that we are going to study. Okay. So solid state, like I said, it is one type of state of matter, okay, in which the intermolecular forces are very strong. Okay, that is what we can say. So let's start with the chapter, the basic understanding about the states of matter you have now. Let's start with the chapter. Write down. Write down in solid, molecules are bonded together in solid, molecules are bonded together with a strong intermolecular force. Right, with strong intermolecular force, and they held at a fixed position and surrounded by other particles and these atoms have and these atoms have only vibrational motion. These atoms have only vibrational motion. Okay, vibrational motion, it's basically to and fro motion. Okay, the particles moves about a fixed position, right? About a fixed position, it will move like this, right? Like this, it moves. Okay, so this is a vibrational motion. Okay, now what are the properties of solids? Properties, the first point, it has definite shape, definite volume, and high density. Okay, like I said, it has high intermolecular force and we cannot compress it. So negligible compressibility. Okay, next property is have high and sharp melting point. Melting point These are the properties of solids we have. Okay. Now, these solids, intermolecular distance, if intermolecular force is high, um, that is possible when the atoms are close, right? So, with respect to distance, we cannot say, because when we say the high intermolecular force, it means the atoms are bonded together, right? So, whatever the distance is, it is bonded already, right? So, atoms are bonded together. So, distance between the atoms, we do not talk here. Okay, yes, but that is true. But that distance is not high. If it is high, then it reduces the force actually. Okay, yeah. So you see, these solids are also classified into two categories. Okay, solids are also classified into two categories. The one is crystalline solid, and other one is amorphous solid. And amorphous solid. Okay, crystalline solids are those solids which has definite and regular shape. Okay, fixed arrangement. Basically here we have fixed arrangement of atoms. In crystalline solid we have fixed and defined arrangement, we can say. Arrangement of atoms. In amorphous solid, there is no ordered arrangement, no pattern, no ordered arrangement of atoms. Means we do not observe any pattern. Okay, no pattern, random arrangement we have here. Okay, so there are a few properties of crystalline and amorphous solid we should know. So we'll see that property first. Okay, so you write down this table, you draw this table. We have properties side, crystalline and amorphous. The first one we'll talk about shape. The second thing is melting point. The third thing is nature. Fourth one is order in arrangement of particles. Particles means atoms or molecules from which it has been made. Anisotropy. We'll see some examples here. Okay. The shape of a crystalline solid, like I said, it is definite and regular. Amorphous solid, it has irregular shape. Irregular shape. Melting point, again, it has definite and sharp melting point. Definite and sharp. And this does not have a sharp melting point, have a sharp melting point, but it melts or softens over a range of temperature. Range of temperature. Nature, this we call it as true solid. When we talk about solid, it means it is crystalline solid. These are pseudo solid. These are pseudo solid. Ordered of arrangement, we have a fixed pattern in which the atoms and molecules are arranged. So we have that long range order, means we have the pattern we can observe for a long range. Okay, long range order. Here we have short range order. This difference also they ask in the exam. Okay, these properties of crystalline solids are directional dependent. Depends on direction. Okay, and this property in which it properties changes with the direction, this kind of property we call it as anisotropy. Okay, and this substance is anisotropic in nature. Anisotropic. Okay, this is properties are independent of direction here. Are independent of direction. And this thing we call it as isotropy. Right? Isotropic substance. These are. Okay. The example of this crystalline solid, we have quartz, we have diamond. Diamond, you know, we have a fixed pattern of carbon atom. Okay. Even NaCl structure also have a fixed pattern. okay, etc. All these are examples of this. Amorphous substance are glass, rubber, plastic, etc. You must have observed that these substances, when you heat this, it melts over a range of temperature. There is no sharp melting point. Okay. Plastic also melts very slowly. You keep on heating it, slowly it melts down. Okay. So these substances are amorphous solids. Okay. They are not true solids. True solids are crystalline, where we have fixed pattern. Okay. Diamond, you must have heard that when you cut the diamond for all these, the jewelry that we made, we cut the diamond in a fixed direction, right? In a fixed direction, you can cut it, right? In one particular direction, it is very difficult to cut the diamond. It is one of the hardest substance we have, but in different direction, you can cut it easily, okay? So this property that is changing with the direction, right? This property, we call it as anisotropy. This phenomenon is anisotropy. And the substance which shows this phenomenon, right, the properties are direction dependent, those substance we call it as anisotropic substance. Okay. So out of all these, the fifth one is the most important property we have. Must keep that in mind. Copy this down, all of you. Done? Please let me know once you finish this. Okay. Okay, yeah. Now, before going into this chapter, let us understand some terms that we'll use in this chapter. Okay. So write down the heading, terms related to a crystal. The first term we use is lattice points. Lattice points. Okay. Write down. It is a point on the lattice. It is a point or place on the lattice at which the atoms, ions, or molecules are present. Points at which atoms, ions, molecules are present. Okay, write down next line. Lattice points are joined together lattice points are joined together by a straight line, by a straight line in order to bring out the geometry of the lattice. In order to bring out the geometry of the lattice. In order to bring out the geometry of the lattice. The another one is crystal lattice. Crystal lattice. Write down, it is the regular 3D arrangement. Regular 3D arrangement of lattice points in space. In space. Third term we have, and that is unit cell. Unit cell. It is the smallest part of the crystal lattice which when repeated in all direction generates the entire lattice. Generates the entire lattice. Okay. Now let us understand this. Three terms that I have given you. Did you write this? Okay, guys, let me tell you one thing here. To understand the concept here, a little bit of visualization is important. Okay, you have to imagine the structure. You have to visualize the structure. Okay, then only you can understand this. Okay, so I'll just let you know when you have to visualize the structure and what you have to do. Suppose I am considering a cube, right? Suppose this is the cube I have. Right? Okay, this is the cube we have. Now, this cube, suppose like this, you have thousands cube. Okay, 1,000 cube you have, similar cube like this. So those 1,000 cubes you can place around this cube. Okay, one above it, one below it, one this side, left side, one right side, one this side in front of you, and one on the back side. Okay, like this you can place the entire cube, like the 1,000 cubes around this cube, and you will get the large structure, right? That large structure is the crystal lattice, which is made up of this one small cube. It is something like, you can understand the matchbox, you can take for an example. However, matchbox is not a cube, it is a cuboid. Okay, but imagine or consider matchbox is a cube. Okay, and you have 100 matchbox, so you can place one after the other matchbox around it, right? One matchbox you put, around that you put the other matchbox, and then above that you can keep on placing the matchbox onto on the each matchbox that is there on the first the level, right? First layer. Okay, so like this, if you generate the entire uh, structure, right, this entire structure is a crystal lattice. Okay, now in this crystal lattice, if you find out the smallest unit, okay, with which the crystal lattice has been generated, the smallest unit is what? The smallest unit is nothing but that one single matchbox. Okay, because the entire lattice is made up of the matchbox, right? The one matchbox. That matchbox is the what? Is the smallest unit with which the entire crystal lattice has been made. So that one matchbox is the unit cell. Okay, is the unit cell, right? So crystal lattice is the arrangement of that 100 matchbox. Okay, in a same manner in all direction, right? And this lattice is made up of, the matchbox is the smallest unit we have, so that one matchbox is the unit cell. Okay, and if suppose some atoms are placed at these points, here we have one atom, here we have one atom, we can have other points also. So wherever the atoms, molecules or ions are placed, this position we call it as lattice point. Where the atoms, ions or molecules are placed. Okay, this cube is nothing but the unit cell. So entire crystal lattice, which I cannot show you here, right, but you can visualize this structure, right? The entire crystal lattice is made up of this cube, and hence this cube is a unit cell. Okay, if you want to study the property of the crystal lattice, you pick up the smallest unit, you pick up the unit cell of that crystal lattice. Whatever the property of unit cell is there, that will be the property of the entire crystal lattice, because the crystal lattice is made up of this unit cell only. Okay, so crystal lattice, how do we get? By repeating the smallest unit in all possible directions. Did you get all this, Tom? Yes. Now you see one thing here. This is the unit cell, cubic unit cell, because the shape is a cube. So it is what? It is a cubic unit cell, we can say. Cubic unit cell, because the shape is a cube, right? Like this, we can have another possibility also. It is not like we always have cubic unit cell. We can take any other possibility. Like for example, if I tell you, for this particular arrangement, if you look at this arrangement, you can consider or let it be this side. I'll draw this side only. Okay. Now, what point I'm trying to make here, if you extend this line this side, right? If you extend this line also on the top, okay. So you can consider this as the x, y, and z axis. You see this? Because the angle is 90°. This is x, this is y, and this is z axis. Okay. Obviously, this cube we have, so it must have some unit, some distance over here, right? Let's see this. This distance on the x-axis, we call it as a. And since it is a cube, so this edge is also a, because we know in cube all edges are same. And even if this edge also, it is the edge length is a only. But for different systems, like if you consider cube, all edge lengths are same. If you consider different system, right, then this edge length will change. Like in cuboid, the edge length is different. Okay. In tetragonal, edge length is a is equals to b, does not equals to c, like this we have. So we can have these three possibilities, right, depending upon the different edges over here. Plus angle also you can consider. In cubic unit cell, what happens, what we can say, or if I write down this way, just a second. Suppose this is A, this I am assuming it as B. Okay. Suppose this is along the z axis, no? So this is B and this is C. Okay. So for cubic unit cell, we know A is equals to B is equals to C. All three edge lengths are same. Even if you consider the angle here, right? This is, suppose we have this angle is beta, this angle is gamma, and this angle is alpha. Opposite to x we have alpha, opposite to y we have gamma, opposite to z we have beta. Okay. So here also we know this fact that alpha is equals to beta is equals to gamma is equals to 90°. This is the three possibilities. For cubic unit cell I'm talking about. Okay, all these are for cubic unit cell. But what happens, we can have different relations possible for A, B, C, for alpha, beta, gamma. Correct? And when you change this relation, like we can have A is equals to B, does not equals to C. Alpha is equals to beta is equals to gamma, does not equals to 90°. Alpha does not equals to beta, does not equals to gamma. Alpha is equals to beta, not equals to gamma. A does not equals to B, equals to C. Right? This kind of various arrangements possible. Right? So all those arrangements gives you one particular unit cell. Okay? All those arrangements gives you one particular unit cell. For cubic unit cell, we have this arrangement. A is equals to B is equals to C, alpha is equals to beta is equals to gamma is equals to 90°. Okay. Mostly in the chapter, we are going to deal with cubic unit cell only. Almost 99% of the cases will deal with cubic unit cell. Okay. So you don't have to worry about the other possibilities much. But one question that they ask in the exam that you should know, that's why I'm discussing this. Okay. Apart from cubic, There is one more unit cell we'll see, and that is hexagonal unit cell. Okay, we'll see that later, hexagonal. But here what you have to understand, that there are different unit cell possible depending upon the relation of A, B, C and alpha, beta, gamma. Correct? Okay. Right. All these unit cell, if you arrange in a proper manner, one after other, you will get an entire crystal lattice. Okay. And if you want to read the property, know the property of the crystal lattice, you have to pick that unit cell from which this lattice has been formed, and the property of that unit cell will be the property of the lattice. Okay, this is what you need to keep in mind. Now, like I said, that there are various possibilities, various unit cell, right, depending upon the relation of A, B, C, alpha, beta, gamma. So let's see what all unit cell we have and what are the possible variations. Okay, so write down the heading. Write down the heading. Seven primitive unit cell. Unit cell and their possible variations. And their possible variations. Okay, I'll show you this table. See this picture, and you have to copy this down. Okay, you don't have to draw these diagram. This below the diagram is given. This you don't have to draw. You just copy down from 1 to 7 and this crystal system, axial length, interaxial angle, and number of lattice in the system. Copy this down. This is structure you don't have to draw. Let me know once you are done. Done? Okay. Now, you see this unit cell. This unit cell is again classified into two categories. Okay. And we call it as primitive or simple unit cell, and the second one is centered unit cell. Okay, centered unit cell. Centered unit cell has again three different types. One is body centered unit cell, body centered unit cell. The another one is face centered unit cell. FC unit cell means face centered unit cell. And other one is end centered unit cell. These three types we have for this. Body centered, face centered, end centered unit cell. Okay. Now each of this crystal system, right? Each of this crystal system has various variations. Like you see, here it is written number of lattice in the system, right? Means this means cubic unit cell if you have, cubic crystal system if you have, cubic crystal system has three different lattice. Okay, one is primitive, which is not written here. One is primitive, other one is body center, and other one is face center. What is this body center and face center? We'll discuss this. Okay, means three possible variations we have in cubic crystal system, keeping A, B, C equal alpha, beta, gamma 90 degree. So this is, you see, this is simple cubic system. This one. When A is equals to B, you see A and B are equal, C is not equal. You'll have this arrangement, tetragonal. Orthorhombic, you see, A is equals to A does not equals to B, does not equals to C, and this is orthorhombic system. Similarly, we can draw this by changing the angle and the edge length. We can have this different types of variations. Okay, so cubic has three different variations. Similarly, tetragonal, you see it has two different variations. Orthorhombic, we have 4 different variations. Rhombohedral, only one. Hexagonal, only one. Monoclinic, 2. Triclinic, 1. Okay, so we can talk about what all variations we have in all these, but that is not important. Okay, they won't ask these variations. I have given you one example of cubic, primitive, body center and face center. Similarly, in tetragonal, we have only primitive and body center. There's no face center. That's why it is 2. Orthorhombic, we have all 4. We have primitive, we have body center, we have face center, we have end center. All 4. That's why it is 4. Rhombohedral and hexagonal, we have only primitive. Monoclinic, we have 2, that is primitive or end center. Triclinic, we have only 1, and that is primitive. Okay, so what you have to keep in mind, those who has only one number of lattice in the system, rhombohedral, hexagonal, triclinic has only primitive units. Okay, the one which has 4, it means it has all 4 types: primitive, body center, face center, end center, depending upon the arrangement of atoms, right? Arrangement of atoms in the crystal unit. But this is not important that what all possible variations we have. The important thing is that the total number of lattice in a system. And these lattice, which is the possible in one particular crystal system, we call it as Bravais lattice. You see it is written over here, Bravais lattice. So total 14 Bravais lattice we have. This question they have asked many times in the exam. Total possible variations is what? Answer is 14. There are 14 different possible variations we have, and this we also call it as Bravais lattice. Okay. Right. This you must keep in mind. However, you can also understand that cubic system has 3 Bravais lattice, tetragonal has 2, orthorhombic has 4, but this kind of specific things they haven't asked yet. They have asked total number of Bravais lattice, which is 14. You must remember that. Okay. Now we'll see these things, this system one by one. Okay. What are the various unit cell and various variations we have over here? Like we have primitive unit cell, body centered, end center, and other things. Okay. So write down the cubic crystal system. The next thing is cubic crystal system. Cubic crystal system. The first one is primitive, or we also call it as simple cubic. Or simple cubic unit cell. Write down. These are the unit cell in which these are the unit cell in which the atoms are present only at the corner. Okay, atoms present only at the corner, right? There are 2-3 things we have to understand here. Okay, first of all, you see, it is cubic unit cell, means you have to draw a cube. We have a cube, and at the corner of the cube, the atoms are present. That is simple cubic unit cell. Okay, that's what the thing is. You have to consider cube here. So I'll show you a diagram first of all, and then we'll discuss few things over here. You see this diagram? See, this is the diagram we have. Atoms are present only at the corner of a unit cell. You see, these are the atoms present. Okay. So like I said, you have to visualize the structure. Okay. You see in this one, in this structure, you see the atoms are not in contact. Okay. Edge length we always represent by small a. Edge length, since it is a cube, so equal edge length we have small a we'll use, right? Did you understand this? Any doubt till now? Because if you have any confusion here, this will disturb you in the next coming sessions also. It's very important to understand this. Till now, there is no any doubt, guys. You can type in CLR if you understood this, whatever we have discussed so far. Correct. Okay. Now you see simple cubic unit cell. What is this unit cell? Atoms are only at the corners. Only atoms at the corners, and the corner atoms are in contact with each other, which is not visible over here. But you should write down this point. The atoms present at the corners are in touch with each other. Atoms are in touch with each other. An atom is assumed to be in spherical shape. And that's why we have voids, vacant space there. Okay, we'll talk about this. Okay, because you see, if the shape of any object is a square like this, you can place one square to other, right? Like this. One sides other like this, you can also place. In that way, you can occupy the maximum space. There's no void present into this. This arrangement of atoms like this won't produce any voids, right? That's why this thing we have. But if the shape is spherical, then no matter how you place the atoms, how perfect you place the atom, there will be some void present, right? So that's why we have void also over here, right? I'll come to this point again, right? So edge length is A, and we are assuming atoms to be spherical. So the radius of the atom we are assuming is small r. Always will have this. Whenever you see r, it is the radius of the atom. A is the edge length of the cube, right? Now, what I said, that atoms at the corners are in touch, which is impossible to show in this 2D diagram. But here you can see this is one cornered atom and this is another cornered atom. These two are in touch. You see this, right? So what is this distance? Can you tell me? And what is this distance? Can you tell me from this corner to this point? Anyone? The distance is R, correct. So this distance is R, this distance is R, and both are in touch. So what is the relation of A and R here?
A is equal to 2R.
2R, right? So for simple cubic unit cell, the first thing that we understood that the relation of A and R is A is equals to 2R. We'll use this relation. In fact, for all other unit cell, we have to establish this relation, A and R relation. Okay. So for simple cubic, A is equals to 2R. Why? Because the atoms are in touch. Okay. Now, if I ask you, this is just one unit cell, guys. This is just the smallest unit. If we talk about the entire crystal, you will have similar units present in all directions. Like this side, we have one unit cell present. On the top, we have one unit cell present. This side, we have another unit cell. This side, bottom, back side, and front side. All side, we have similar unit cell present. Sharing these atoms, coordinate atoms in these unit cell. Okay, so you see when you place this atom over here, does this atom completely within the unit cell? It is present completely within the unit cell. Is it this atom at the corner? Suppose if I place an atom, one simple example I'm taking, suppose if I place an atom at the body center of this unit cell, somewhere here. So this atom is within the unit cell, right? Yes or no? This atom is within the unit cell. Please respond, guys. I need your cooperation here, because if you do not talk, I won't understand whether you are getting it or not. Right? This atom present within the unit cell. Okay. But can we talk the same thing about this atom? Is this atom present within the unit cell? No, because some part of it is outside the unit cell, right? Right, some part of it is outside the unit cell. So if I ask you, what part of this atom present within the unit cell, right? So whatever the part which is present within the unit cell, that is the contribution of this atom in this unit cell. Are you getting it? Means suppose if I ask you the total number of atoms present in one unit cell, the question is this: total number of atoms present in one unit cell. I want all of you to respond. I want all of you to respond. Total number of atoms present in one unit cell. Tell me, guys, fast.
1.
Is it 1? Okay, I'm getting one of the response. I'm getting 8. What about others? Please respond, guys. 4, 2, 7. So I got 5 responses and all different. 1, 2, 7, 4, 8. Again, 1, 4. Okay. Madhya is getting 1. Okay, fine. See, guys, first of all, if I ask you, okay, Shashwini is saying 8. Fine. See, guys, if I ask you, what is the total? First of all, this you ignored, this part. This is, just a second. I have to delete this. Wait. Right. Just a second. This I have removed. So total number of atoms in one unit cell. So first of all, there are 8 atoms present at the corner, but the answer is not 8 because the atom is not completely within the unit cell. Like I said, some part of it is outside the unit cell. So a number of atoms in one unit cell will count only that part which is present within the unit cell. Are you getting it? We'll count only that part which is present within the unit cell. Okay. So how do we find out here that what part of this atom present within the unit cell? That is the question. Okay. Now we'll discuss this point over here, but I want to ask one more question over here. Could you tell me, in the crystal, I'm not talking about one unit cell, in the crystal, with this corner or any one of the corners, suppose I'm taking this example, this corner, with this corner, how many cubes you can draw? Could you tell me? How many cubes you can draw? Only 3? Okay, I'll explain this, wait. See, with this corner, suppose, and listen to me very carefully, okay? With this corner, can we place a cube this side in front of this face? Yes or no? You can type Y quickly. Can we place a cube this side which has this corner common in front of this? Yes. We can, so one cube is already this, another one in front of this face. So we have 2. Another one we can place besides this face, this side, right? That is 3. And one more cube we can place with this edge, means in between this cube and this cube, we'll have somewhere over here with this common edge. We can place one cube this side. So we have in this plane, you see, in this plane, we have 1, 2, 3, and 4 cubes present. Yes or no? Is it clear? You can also understand this way. Suppose wherever you are sitting in now, you must be in a room, right? Consider the room as a cube. Okay, listen to me very carefully. It's very difficult to explain these things in online classes. Okay, that's why I am repeating this again and again. What I'm telling you, that consider the cube, the room where you are sitting in, as a cube. Okay, and how many corners are there in that cube where you are sitting in? There are 8 corners, right? 4 on the top and 4 on the bottom, right? 4 on the roof and 4 on the floor, right? On the bottom, correct? So you consider any one top corner, okay? Any one corner you take, okay? And you imagine with that corner, how many different such rooms you can draw. You can see on the left side, you can draw one. On the back side, you can draw one. On the corner, you can draw one. Diagonally, you can draw one. So there are 4 different rooms you have in this particular floor, right? In one particular floor, you can have 4 different rooms with one particular corner. Yes or no, guys? Can you imagine that? Right? So these 4 rooms are there in one floor, right? Still the half part of the atom is present on the other floor, like the next floor that you have. So suppose you are in the ground floor. So if the same 4 rooms, if you assume above the room where you are sitting in, right? So you will have 4 rooms on the first floor also, the top floor also, right? So that 4 rooms on the top floor, 4 rooms on the bottom floor, and the center of this 8 rooms will be this corner. Yes or no? Center of these 8 rooms will be this corner. Yes or no, guys? Just you have to visualize this. Okay. You can actually draw 8 different cubes with one particular corner. Right? Yeah. Hello? Right. So if you take the example of this one, we have 4 cubes here, 1, 2, 3, and 1 given one, 4 cubes. and 1 above this cube, 5, 1 above this cube, 6, 1 above this cube, 7, and 1 above this cube, that is 8. So with one particular corner, we can draw 8 different cubes. And that's why what we say, the contribution, this is very, very important, and you have to memorize this. The contribution of one atom present at the corner in a unit cell. In a unit cell. Okay. Since this atom is distributed among 8 unit cell, 4 in this plane, 4 on the top plane, right? This atom is distributed among 8 unit cell. It means the contribution in 1 unit cell is what? 1 by 8. Did you get it? Did you get it? I want you to respond, guys here. Please tell me, did you get it? The contribution of one atom in 1 unit cell is present at the corner is 1 by 8. Correct? So means this means what? This means what? That only 1 by 8th part of this atom is within this unit cell. Present within this unit cell. Only 1 by 8th part of it. Right? That's why when we count the total number of atoms, we cannot take the entire atom over here. We cannot say 1 plus 2 plus 3 plus 4, 5, 6, 7, 8. Oh, there's one thing is missing here. I just saw this now. One atom should be here also. It is missing. Anyways, right? So we cannot say 8 because we have 8 atoms at the corner, but only 1 by 8th part of it is present within the unit cell. So what is the total number of atoms within the unit cell? The answer will be what? The answer will be there are 8 corners, there are 8 atoms, and 1 atom contributes 1 by 8 into the unit cell. Hence, there are effectively only 1 atom present in the unit cell. Is it clear? Yes. Understood? So what you have to keep in mind that the corner atoms contributes 1 by 8, right? This you have to memorize, very important. Okay, one thing is this. Another thing is, since we know the total number of atoms is 1, then what is the volume occupied by these atoms? That is 1 into 4 by 3 pi r cube. One volume, the one atom, the volume is 4 by 3 pi r cube. Why 4 by 3 pi r cube? Because we have assumed it is a spherical shape, right? So the volume of one atom which is present within the unit cell is 4 by 3 pi r cube. So can we say the volume occupied by the atoms in this unit cell is 4 by 3 pi r cube? Can we say that? The volume occupied by the atoms in this unit cell is 4 by 3 pi r cube? Yes. It should be the number of atoms into the volume occupied by one atom. So, right? So volume occupied by one atom of radius r is 4 by 3 pi r cube. And number of atoms is 1. Total volume occupied by what? 1 into 4 by 3 pi r cube. Yes? What is the volume of the cube? Can you tell me?
A cube.
A cube, right? Means what? This is the volume available. A cube is the volume available, right? But since the shape of the atoms is spherical, so it cannot occupy the entire volume. Means AQ is the total volume, But atom won't occupy the entire volume because of the shape is spherical. I have already discussed it, that when you arrange the atom, there will be some vacant space, some void is present, right? Like you see, here is the void. This is the void we have here. This is the void we have here. So volume is A cube, but the total volume is not occupied by the atoms. Even if you see here also some void we have on the top, right? This side some void, this side some void. On the bottom also we'll have some void which is not visible from this side. Okay, so we can surely say that atom does not occupy all the space. Yes or no? There will be some vacant space available. Yes?
Yes, sir.
Okay, so next is what? Next we'll find out the packing fraction here. Means what volume is occupied by the atoms. This we call it as packing fraction. Packing fraction is represented by phi. Okay, represented by phi. Write down the definition of it. It is a total volume. It is a fraction of total volume. Write down. It is a fraction of total volume occupied by the constituents particles right? So packing fraction PF is equals to, we can write volume occupied by the atom divided by volume of unit cell. Correct? So volume occupied by the atoms is what? Number of atom. One thing I forgot to tell you here, the number of effective atom that we calculate here, this, the number of effective atom, this we call it as the rank of the unit cell. Okay, rank of the unit cell, represented by Z. Effective number of atoms, that is the rank of the unit cell, represented by Z. Okay, so what we can say here, see, volume occupied by the atoms, what we can say, it is ranked into the volume of one atom, that is the total volume of the atom, divided by the volume of unit cell is a cube, so it is A cube. Rank is 1, volume of one atom is 4 by 3 pi r cube, whole divided by A cube. We know A and R relation, and that is A is equals to what?
2R.
2R. So 2R cube. And when you solve this, you see R and R will get cancelled. And the value that you get here is 0.524. Right? Means the percentage packing efficiency is 52.4%. Means this is a percentage of volume occupied by the atoms of the unit cell. Okay. Void fraction, if you find out, void fraction, what is the vacant space? Void we have, that is 1 minus 0.524, that is 0.476. Percentage void is equals to 47.6%. So this is the percentage of volume occupied by the atoms in the simple cubic unit cell, and this is the volume that is available vacant. Any doubt?
No, sir.
Right. There is one more term. Did you write this, all of you? Okay. There's one more term in this, and that we call it as, write down, coordination number. Coordination number. Write down the definition of it. It is a number of nearest it is a number of nearest atom which are in contact, which are in touch, which are in contact. Tell me, what is the coordination number of simple cubic unit cell? Number of nearest atom are in touch. Just you need to count. Tell me. Anyone? What is the coordination number? See, simple cubic unit cell is what? We have atoms present here at the corner. 1, 2, 3, 4, 5, 6, 7, and 8. Right? So could you tell me how many atoms are in touch with? How many atoms are in touch or contact with this atom? We know the edge length A is equals to 2R, right? Means these two atoms are in touch. Yes or no? These two atoms are in touch. These two atoms are in touch. So atoms present at the adjacent edges are in contact with each other, right? So yes or no? A is equals to 2R, the relation is true, and that means the atoms at the adjacent corner are in contact. Yes or no, guys? Right. So this atom is in contact with 1, 2, 3. Do we have any other possibility? Because you have to consider the entire lattice. Okay, so we have one atom present this side also in this cube. When you extend this edge, okay, we have an atom present somewhere here. This too also follows the same thing. A is equals to 2R relation. So fourth one is this, right? When you extend this edge, what happens next? When you extend this one on the top, we have one cube on the top also, right? Because you have to consider the entire lattice. One cube we have somewhere here. So this is the fifth one, right? And when you extend this edge in this direction, imagine this is coming towards you. So we'll have an atom here, which also in touch with this particular atom, right? So we have 1, 2, 3, 4, 5, and 6. So coordination number in case of simple cubic unit cell is 6. Is it clear? Right, so for coordination number, you have to consider the lattice, not the simple unit cell. Can I move on? Okay, so what all things we have discussed? We have discussed here the first of all the relation of A and R. So simple cubic unit cell A is equals to 2R, the first thing we have discussed. We have discussed the rank of the unit cell. Rank is nothing but Z, and Z is equals to 1. We have discussed about the packing fraction, and packing fraction is 0.524. We have discussed about the coordination number Cn, and that is 6. These 4 things you need to find out for other unit cell also, which we are going to see. That is BCC and FCC, body centered cubic unit cell and face centered cubic unit cell. Okay, so let's discuss the next thing here. That is body center cubic unit cell. Okay, write down in this unit cell, we also call it as BCC in short. Write down in this unit cell, the atoms are present at the corner. In this unit cell, the atoms are present at the corner along with an atom at the body center. Along with an atom at the body center. Okay, means in primitive unit cell, one more atom you placed at the body center. It is something like this. The room in which you are sitting in, you assume the 8 corners has one atom, and at the center of the room we'll have another atom, that is BCC. Okay, so simple cubic unit cell is atoms only at the corner, right? The room in which you are sitting in, the 4 cornered atoms of the room. 8 corner atoms of the room, 4 on the top, 4 on the bottom, right? That contains atom, that is simple cubic unit cell. And one more atom, if you place at the body center, it becomes body center cubic unit cell. Now, because of this atom present at the body center that you placed, because of this, what change happens here that we'll see. Okay, so look at the diagram first of all. See this. The atoms at the corner plus atoms at the body center. You see this one. Now what happens since you place this atom over here, and here we do not have that much space, so that it accommodates the same size of atoms. All atoms have the same radius. So this body center atom push the all other atoms in outward direction. So what happens, it is something like this. This body center atom push all other atoms in outward direction like this. And hence the corner atom loses its contact. You see, there's no contact in the corner atom. There's a gap here. Between these two corner atoms, there's a gap here, right? So corner atoms are not in touch. And when the corner atoms are not in touch, so what we can say? We cannot say that relation of A and R is equals to A is equals to 2R. This relation is not right because atoms are not in touch, corner atoms. Okay. But first thing is what? That atoms along the body diagonal are in touch. We have an atom present over here also. Atoms along the body diagonal are in contact. See, there are two types of diagonal here, right? There are two types of diagonal. One is this diagonal. This diagonal is along this face. This is face diagonal. And body diagonal, what you need to do, you have to take one atom on the top corner, like suppose this atom you have taken, this atom with body center and this atom. This is body diagonal. Could you tell me how many body diagonal possible? How many body diagonal possible in a cube? Yes, we have 4 body diagonal possible. You can understand this easily. No, it's 4. 2 corners gives you 1 body diagonal. So 8 corners gives you 4 body diagonal. So we have 4 body diagonal. So we have two different things. One is body diagonal, other one is face diagonal. Face diagonal is the diagonal of a face. This is the face of the cube. This is the face of the cube. This is the face of the cube, right? Diagonals of a face. So what we say, atoms at the corners are not in contact, but as you can see this from this corner to this corner here. This corner to this corner, you see along the body diagonal, along the body center, these atoms are in touch, these 4 atoms. So what we can say, write down atoms along the body diagonal are in contact. What is the length of the body diagonal in terms of R radius? What is the length of the body diagonal? Tell me.
R is equal to A root 3 by 4.
A root 3 by 4. Okay. Okay. You see this? This is the phase diagonal. This is the phase diagonal. And this is the body diagonal. From this corner, one from the bottom and one from the top, like this. This is the body diagonal. Okay. We know the edge length here is A. And this edge length is also A. What is this angle here? 90 degree. Because it is a cube. Right? This is the cube. Okay. This is A. This is A. So phase diagonal is what? Is using Pythagoras theorem, we can write A square plus A square root over of it. That is A root 2. Correct? Phase diagonal is. Remember this. We won't calculate this again and again. Okay. Keep this in mind. Phase diagonal is A root 2. Body diagonal, if you see, body diagonal is this, the yellow one. This is A root 2. This is A, right? And this angle is also 90 degree. So it is root 2A square plus A square root over of it. Again, Pythagoras theorem. So it is 2A square plus A square. So we have A root 3 is the body diagonal. Right? And we know along the body diagonal, the atoms are in contact. So this is R plus 2R plus R, that is equals to 4R. So in terms of radius of atom, if you write, body diagonal is equals to root 3A is equals to 4R. So R and A relation here is R is equals to root 3A by 4. That is the relation we have. Okay. So we have done R and A relation. That is root 3A by 4. R is equals to. Second thing is the rank. Could you tell me the rank of the unit cell here? Effective number of atoms?
2.
Because you have 8 corners, contribution is 1 by 8 and 1 in the body center. So that is present within the unit cell. Contribution is 1. So that is 2. So total number of atoms we have. Okay. Now, the packing fraction is what? It is the rank into the volume of the this thing. 1 atom divided by volume of cube, A cube. So 2 into 4 by 3 pi. R we can substitute as this. Divided by AQ. And when you solve this, you'll get 0.68 packing fraction, and void fraction is 1 minus 0.68, that is 0.32 fraction. Clear? Any doubt? Okay. The last thing here is coordination number. What is the coordination number? Could you tell me?
8.
8. Because you see the body center, you see this in touch with 4 on the top and 4 on the bottom. Okay, with this you can understand it easily. So coordination number is 8 here. Clear? Okay. Okay. One question you see, a molecule forms with the atom A and B, right? And forms BCC arrangement, where all A atoms present at the corner and B occupy the body center. Find the formula. Find first one, the formula of the compound. Second one, formula if all atoms along a face diagonal has been removed. Try these two questions. No, it's BCC. So A is equals to 2R is not possible. And the question is not about that. The question is the formula of the unit cell. Means you need to find out the contribution of the two atoms, A and B. And then you have to write down the formula. See, actually, this type of question is very common. I'll do this. Wait. See, all atoms A occupies corner, right? A at the corners. So what is the effective number of atoms of A? We know A at the corners, so it contributes 1 by 8 into the unit cell, so into 8. So 1 A atom present in the unit cell. Similarly, B, if you find out for first case, B at the body center, so that will be 1 into 1 and 1 in the contribution. So effectively, there is 1 A atom present and 1 B atom present. Hence, the formula is AB, assuming A is the cation and B is the anion. Right? Because A is 1, B is 1, so formula is AB. Now, in the second question, what happens? Atoms along the phase diagonal has been removed. Means if you go along the phase diagonal, what all atoms you will get? Along the phase diagonal, what all atoms you will get? You'll see this. Here we have A present, A present, A present. So any phase diagonal you see, what all atoms has been removed? Any phase diagonal, only A atoms will be removed, right? Yes. So there are 2 A atoms has been removed now. It is not present in the unit cell, right? Then how many atoms are present? Total. How many atoms are present then? Total A. Out of 8, 2 has been removed. It means 6 A atom is present. Hence, the contribution of A in the second case, contribution of A in the unit cell is equals to, we have 6 atom presents and contribution of one of the A atom is 1 by 8 because it is at the corner. So it is 3 by 4. And B, the contribution is 1 because there is no change in B, body center. So here the ratio is what? A 3 by 4 and B. Or if you want to simplify this, the formula is A3 B4, the molecular formula. This is the answer. Did you get it? Any doubt? Right? This is how we'll find out the formula unit of any crystal depending upon what atoms present at what position. Okay. We did not talk about face-centered cubic unit cell. Okay. We don't have time now for this. Okay. So next class will start with face-centered cubic unit cell. Okay. You can write down the heading. We'll start from this next class. Okay. Let me know next class. We have to start FCC unit cell. Okay. Thank you guys. Thank you.
Thank you, sir.
Thank you,
Thank
sir.
you, sir. Thank you, sir.